Hello students, today we are going to discuss about ethers and epoxides. What are called ethers and what are called epoxides? Before we discuss epoxides, we will discuss about ethers. As you know already about the general formula of ethers, R bond O bond R. R bond O bond R is the general formula of ethers where R represents alkyl group. So we can also say that ethers are nothing but dialkyl derivatives of water. Dialkyl derivatives of water. Because you know the formula of water H2O, H bond O bond H. When we replace the two H atoms of water molecule by alkyl groups, we get R bond O bond R. Therefore, ethers can be considered as dialkyl derivatives of water. Otherwise, ethers may also be considered as alkyl derivatives of alcohol. As you know, the molecular formula or general formula of alcohols is R bond O bond H. When we replace H atom of an alcohol by alkyl group, ROH becomes ROR. Therefore, we can say that ethers are alkyl derivatives of alcohols. So ultimately we can say ethers may be considered as alkyl derivatives of alcohols or dialkyl derivatives of water. Ethers contain R bond O bond or linkage. Ethers are classified into two types. They are symmetrical ethers and unsymmetrical ethers. What are called symmetrical ethers and what are called unsymmetrical ethers? The ethers which contain similar alkyl groups are called symmetrical ethers. They are also called simple ethers. Examples for simple ethers: dimethyl ether, dimethyl ether, CH3 bond O bond CH3. Second example, diethyl ether, C2H5 bond O bond C2H5, or ET bond O bond ET, dimethyl ether, diethyl ether. These are the examples for simple ethers. Since they contain similar alkyl groups, they are also called symmetrical ethers. Now, what are called unsymmetrical ethers? The ethers which do not contain similar alkyl groups. In other words, the ethers which contain different alkyl groups are called unsymmetrical ethers. R is not equal to R dash. R is not equal to R dash. Means unsymmetrical ethers contain two different alkyl groups. Two different alkyl groups means methyl ethyl or methyl propyl, etc. Unsymmetrical ethers are also called mixed ethers. Examples for mixed ethers: ethyl methyl ether, ethyl methyl ether, C2H5 bond O bond CH3, or CH3 bond O bond C2H5, ethyl methyl ether. Second example for mixed ethers is methyl phenyl ether, CH3 bond O bond C6H5. These are the examples for mixed ethers. Mixed ethers contain different alkyl groups. In IUPAC system, Ethers may be named as alkoxanes. Alkoxanes. For example, dimethyl ether. Its formula CH3 bond O bond CH3. The IUPAC name of dimethyl ether is methoxymethane. Methoxymethane. Similarly, the IUPAC name of diethyl ether is ethoxyethane. English alphabetical order must be followed while writing the common names of mixed ethers. Ethyl methyl ether. Ethyl methyl ether. Since E comes before M, ethyl must come before methyl. Similarly, methyl phenyl ether. M comes before P, therefore methyl phenyl ether. IUPAC name of ethyl methyl ether. Oxygen atom must be attached with the smaller alkyl group. The correct IUPAC name of ethyl methyl ether is methoxyethane. Methoxyethane. Now, the IUPAC name of methylphenyl ether is methoxybenzene. Methoxybenzene. So, whenever we write the IUPAC name of mixed ethers, oxygen must be included along with the smaller alkyl group. Simple ethers assigned common names. Name both alkyl groups bonded to the oxygen. Arrange these names alphabetically and add the word ether. Already we studied this one. For symmetrical ethers, name the alkyl group and add the prefix di. Example is given: secondary butyl methyl ether, secondary butyl methyl ether, next diethyl ether. One is named as a hydrocarbon chain, the other is named as part of a substituent bonded to that chain. Name the simpler alkyl group as an alkoxy substituent by changing the "-yle" ending of the alkyl group to oxy. Name the remaining alkyl group as an alkane with the alkoxy group as a substituent bonded to this chain. Common alkoxy groups: methoxy, ethoxy, tertiary butoxy. Let us see the IUPAC names of few organic compounds: CH3, CH2, CH2O, CH3. 1-methoxypropane. 1-methoxypropane is the IUPAC name of this compound. CH3, CHO, CH3, CH3. 2-methoxypropane. CH3CH, CH3O, CH3, CH, CH3. 2,2-propoxypropane. Now, cyclic ether. Epoxides, alkane oxides. Cyclic ethers are also called epoxides. They are three-membered compounds. Example: H2C bond CH2 bond O, ethylene oxide, epoxyethane, ethene oxide. Propylene oxide 1 comma 2 epoxy propane 1 comma 2 propene oxide. Butylene oxide 2 comma 3 epoxy butane 2 comma 3 butene oxide. Cyclic ether tetrahydrofuran tetrahydrofuran tetrahydropyran. Ethers exhibit metamerism. Ethers exhibit metamerism. For understanding metamerism, let us take one example. CH3, CH2O, CH2, CH3, that is a diethyl ether, methyl propyl ether, CH3, CH2, CH2O, CH3, methyl propyl ether. Ethers exhibit metamerism. There are two metamers for the compound containing 2 carbon atoms, 6 hydrogen atoms, 1 oxygen atom. It means compound having molecular formula C2H6O may have two metamers. They are diethyl ether, methyl propyl ether. Metamers contain different alkyl groups. Metamers differ in the alkyl groups attached with oxygen. In diethyl ether, ethereal oxygen is bonded with two ethyl groups, whereas in methyl propyl ether, ethereal oxygen is bonded with a methyl and a propyl group. So the compounds which differ in the nature of alkyl groups bonded with oxygen are called metamers, and the phenomena is called metamerism. So ethers exhibit metamerism. Ethers also exhibit function group isomerism. Ethers also exhibit function group isomerism. For example, the compounds having the molecular formula C2H6O may have two function group isomers. They are ethanol and dimethyl ether. Ethers exhibit function group isomerism. Molecular formula of ethanol and dimethyl ether is the same, C2H6O, but the function groups present in these two compounds are different. Ethanol has alcoholic function group, whereas the dimethyl ether has ethereal function group. So, ethers exhibit two types of isomerism. Number one, metamerism, and number two, function group isomerism. Preparation of ethers. Ethers can be prepared by the dehydrogenation of alcohol. Ethers can be prepared by the dehydrogenation of alcohol. Second one is industrial synthesis for diethyl ether. Industrial synthesis for diethyl ether. Here, dehydrogenation means removal of hydrogen. By the removal of hydrogen from alcohol, we get ether. Similarly, diethyl ether can be synthesized industrially by treating ethyl alcohol with sulfuric acid. When ethyl alcohol is heated with sulfuric acid at about 140 degrees centigrade, gives diethyl ether. This is one of the methods to prepare diethyl ether. By the dehydration process of ethyl alcohol, diethyl ether can be obtained. Now, SN2 mechanism, not generally useful for the synthesis of ethers in the lab. Only symmetrical ethers can be made this way. Conditions are very compound specific. At 180 degrees, ethanol would yield ethylene instead of the ether. Means it is a temperature controlled reaction. If the temperature is reached beyond 180 degrees centigrade, then instead of ether we get ethylene. Williamson synthesis. Reaction between a metal alkoxide and alkyl halide. As you know already about Williamson synthesis, the best method to prepare ethers is Williamson synthesis. What is Williamson synthesis? When sodium alkoxide is treated with an alkyl halide gives an ether. When sodium alkoxide is treated with an alkyl halide gives an ether. RONA plus RX gives rise to ROR plus NaX. RX should be CH3 or a primary alkyl halide. SN2 mechanism. SN2 mechanism is involved in the Williamson synthesis. Cyclopentoxide ion. Cyclopentoxide ion on treating with methyl iodide in the presence of tetrahydrofuran solvent gives cyclopentyl methyl ether. Now physical properties of ethers. The oxygen which is present in diether ether or the oxygen which is present in ethers is sp3 hybridized. Bond angle in ether molecule is 109.5 degrees, approximately 109.5 degrees. Ethers are polar, no hydrogen bonding. Ethers are polar, no hydrogen bonding. Polarity occurs because of the high electronegativity of oxygen. Though ethers are polar, hydrogen bonds do not exist between the molecules of ether. That is the reason the boiling point of ethers is below 0 degrees centigrade. Melting or boiling points are moderate and ethers are water insoluble. Why ethers are water insoluble? Because ether molecules cannot form hydrogen bonds with water molecules. Ethers and epoxides exhibit dipole-dipole interactions because they have a bent structure with two polar bonds. Diether ether is a very important organic solvent. Diether ether is polar in nature. It is water insoluble. Its boiling point is 35 degrees centigrade. Very inflammable and forms explosive peroxides. Here, diether ether is very flammable. Diether ether is very flammable, readily catches fire and forms explosive peroxides. Now, we come to the chemical properties of ethers, chemical reaction of ethers. When we observe the structure of ether molecule, ethereal oxygen has two lone pairs of electrons. Therefore, ether molecule can donate lone pairs of electrons to any other molecule and can form coordinate covalent bond. According to Lewis theory of acids and bases, any molecule or ion that can donate a lone pair of electrons to the other molecule and forms a coordinate covalent bond is called a base. Therefore, ether acts as a Lewis base. Due to the presence of two unshared pair of electrons or lone pairs of electrons, ethers may exhibit basic property. Like ammonia is a base, similarly ethers may also be considered as bases. Ethers form etherates with Lewis acids such as BF3. What is BF3? Boron trifluoride. Boron trifluoride is a Lewis acid. Why? Because B atom has an empty 2p orbital. It can accept a lone pair of electrons from any other molecule and can form a coordinate covalent bond. Therefore, BF3 may act as Lewis acid. Now, diethyl ether molecule can donate a lone pair of electron to B atom of BF3 and can form a coordinate covalent bond. Therefore, diethyl ether may act as a Lewis base. Chemical reaction of ethers. Basic property: oxonium salt with cold concentrated inorganic acid. Ethers react with hydrochloric acid at about 273 Kelvin temperature, form dialkyl oxonium chloride. Diethyl ether reacts with HCl. Example for this reaction: when diethyl ether reacts with HCl at about 273 Kelvin temperature gives diethyl oxonium chloride. Chemical reaction of ethers. Acid cleavage. An ether reacts with concentrated hydrogen halide, gives alkyl halide and alcohol. If excess of hydrogen halide is used, the alcohol formed reacts further to give alkyl halide. ROR plus concentrated HX gives rise to RX plus R dash X. X may be bromide or chloride. Reactions of unsymmetrical ethers. When alkyl group of an ether is primary or secondary. When an alkyl group of an ether is primary or secondary. SN2 mechanism. It follows SN2 mechanism. Nucleophile attacks the least substituent carbon of oxocation. Look at the equation. In this equation, ethyl methyl ether reacts with hydrogen iodide, forming oxocation. This oxocation reacts with iodide ion, giving alkyl halide. If excess of hydrogen iodide is used, mole is converted to ethyl iodide. So this is a reaction of ethyl methyl ether with HI. Ethyl methyl ether reacts with HI, forming methyl iodide and methyl alcohol. If excess of HI is used, then this ethanol is converted to ethyl iodide. Epoxide. Preparation of epoxide. Epoxidation of alkene. Reaction of alkenes with peracid. When an alkene reacts with peroxy acid, forms epoxide. Along with epoxide, we also get an acid. Epoxides are also called oxidanes. Mechanism is also mentioned. Epoxidation of alkene. Examples of epoxidation. Here, peroxyacetic acid is taken for example. Peroxyacetic acid reacts with peroxybenzoic acid, When peroxyacetic acid is treated with peroxybenzoic acid gives metachloroperoxybenzoic acid. Metachloroperoxybenzoic acid. When cis-2-butene reacts with peroxyacetic acid gives an epoxide. Similarly, when trans-2-butene reacts with peroxyacetic acid also gives an epoxide. Preparation from halohydrin. Preparation from halohydrin. Addition of HOX to an alkene gives a halohydrin. Treatment of a halohydrin with base gives an epoxide. Intramolecular Williamson ether synthesis. This reaction is an example for intramolecular Williamson ether synthesis. Example is also given. Industrial synthesis of ethylene oxide. Industrial synthesis of ethylene oxide. Controlled oxidation. Controlled oxidation of ethylene over a silver catalyst. Controlled oxidation of ethylene over a silver catalyst gives ethylene oxide. Formation of ethylene oxide is an exothermic reaction. Excessive rise in temperature and over-oxidation gives complete combustion liberating H2O and CO2. High temperature cause degradation of catalyst. High temperature cause degradation of catalyst. Silver or Al2O3 also acts as a catalyst. One example is given. Reaction between ethylene and silver oxide. Ethylene reacts with silver oxide in the presence of O3 gives ethylene oxide. This is the formation of ethylene oxide or epoxide. Ethylene oxide can be obtained by treating ethylene with oxygen. This is the oxidation of ethylene. When ethylene is oxidized in the presence of a catalyst, silver oxide gives ethylene oxide. This ethylene oxide is also called epoxide. Previously we studied about preparation from halohydrin. Cyclohexene was taken as an example. When cyclohexene is treated with chlorine in the presence of water gives trans-2-chlorocyclohexanol. This trans-2-chlorocyclohexanol on treating with NaOH gives an intermediate compound. Ultimately, this intermediate compound is converted into 1,2 epoxy cyclohexane. So this is also one of the methods to prepare an epoxide from halohydrin. After this already we studied about industrial synthesis of ethylene oxide. Ethylene oxide can be synthesized on a large scale by controlled oxidation of ethylene over a silver catalyst. The reaction between ethylene and oxygen is highly exothermic. Excessive rise in temperature and over-oxidation causes complete combustion liberating H2O and CO2. High temperature causes degradation of catalyst. In this reaction, silver oxide may be used as a catalyst Otherwise, silver may also be used as a catalyst. Silver or alumina Al2O3 may also be used as a catalyst. Thank you.